Welcome back. So today we're going to have lecture number 23, which is entitled The Nature of the Atom, and we're going to be talking about the structure of the atom. How are atoms made? First of all, the idea that there are such a thing as atoms, in other words, that matter is broken down into these very, very small, indivisible particles. That's what atom means. Atom means cannot be divided. The idea of the atomic theory goes back thousands of years. In particular, Lucretius, who wrote De Rerum Natura, which means on the nature of things, described his ideas about atoms. And his idea was that the structure of macroscopic objects kind of mimicked or came from the structure of the microscopic objects. So that, say, atoms of air were very soft and fluffy, and atoms of water were very smooth and could flow over each other, and atoms of fire were sharp and prickly, and that's why they hurt you if you tried to touch it. What we're going to talk about today is then some more modern ideas about the atoms. And first, the J.J. Thompson model of the atom, which is sometimes referred to as the plum pudding model of the atom. J.J. Thompson, who lived from 1856 to 1940, developed what is called the Thompson model, or sometimes the plum pudding model of the atom. His idea was that an atom is basically this positively charged round part, and then scattered throughout the positive charge are these negative, very tiny charges, kind of scattered throughout the overall positive section, positive charge. Kind of like raisins scattered throughout a plum pudding. So the negative charges were kind of like the raisins, and the pudding was the positive part. Now, this developed some problems, or some problems with this model were recognized when Ernest Rutherford did some scattering experiments. So here's a drawing of Rutherford scattering, and I do apologize for having so many drawings rather than overheads, because we are right in the middle of the coronavirus outbreak, and we're having some computer difficulties, so I've got to draw a lot of these things by hand. So Ernest Rutherford, who lived from 1871 to 1937, did this experiment in 1911 that's now referred to as Rutherford scattering. He took a radioactive source that gave off alpha particles. Now, we've mentioned alpha particles before. Keep in mind, and for my class, you need to remember this, an alpha particle is a helium nucleus, which is made of 2 protons and 2 neutrons. So it has a +2 electrostatic charge. So remember that. So giving off these alpha particles in all directions, the beam was collimated by having a lead screen with a small hole in it here, which would only allow alpha particles to go in a particular direction. They would then strike a target, sometimes gold foil was used. It would strike the target, and then for every alpha particle there would be this shower of particles typically coming out the back that would then strike a screen and could be studied. Now, what happened was, every now and then, some particles would be scattered backwards. They would come back toward the source. These are called backscattered. Well, this was a very, very big surprise. Rutherford actually said in 1911, it was almost as incredible as if you had fired a 15-inch shell at a piece of tissue and it came back and hit you. So this was a very big surprise. Well, why? What was such a surprise about it? Well, let's go back to the Thompson model and see why this would be a surprise. So remember the Thompson model of the atom, which had this positive charge spread out throughout the whole thing, the pudding part, and then the negative charges were the little raisins scattered out and much smaller. Now we've got this alpha particle, which is the +2 particle coming in, striking the nucleus. Well, there is no strong positive charge that would repel this alpha particle and send it back this way. There's nothing there that would cause the alpha particle to go backwards. Well, what Rutherford had to do was to take the positive charge and condense it down into a smaller region that would give enough force to send the alpha particle back the way it came from, to backscatter it. What Rutherford did in the Rutherford model of the atom, sometimes referred to as the planetary model, was he took all of this positive charge and compressed it down into a very small, dense positive charge at the center of the atom, what we now refer to as the nucleus. The negative charges the rasons in the Thompson model, what we now call the electrons, he then had orbiting around the nucleus very much like the planets orbiting around the sun, which is why it's referred to as the planetary model. But let me emphasize that the electrons going around the nucleus are much, much further away than the nucleus from the nucleus than this scale would indicate. The atom is really much, much more vastly empty space. So just imagine these electrons are much, much further away. So there we have the planetary model of the atom. But the question arises, can these electrons orbit the nucleus at any distance? Could we have an electron at half this distance, or twice this distance, or 3 times this distance? Or is there something limiting the distances that the electrons can actually orbit the nucleus? Well, let's take a look at another light source. Earlier we looked at an incandescent light source that gave off a continuous spectrum, a blackbody spectrum, or almost a blackbody spectrum. Let's look at another type of a light source and see what kind of light that gives off. Let's look at the light source of the simplest kind of element, hydrogen. Here I have a light bulb, a very narrow light bulb that has hydrogen inside. So you can kind of think of this like a neon light bulb, but rather than neon, it's hydrogen. When I send electricity through it, it illuminates. Now let's imagine that we could take this light and separate it out into its constituent colors, kind of like we did with the incandescent bulb to get the continuous spectrum with all of the colors. What would the rainbow, so to speak, what would the spectrum look like for hydrogen? Here we see the emission spectrum of hydrogen. We do not see all of the colors of the rainbow. We can see, and most of the time when I've had students look at this, they can see 3 of these colors. The 4th is a little bit hard to see. There is a red line over here, then there's a bluish green line, a blue line, and some people can see a purple line over here, but it's much harder to see, I think. So we can see maybe 3 colors, maybe 4 colors. Well, what's going on here? Why is hydrogen only giving off these certain colors? Well, certain colors correspond to certain wavelengths or certain frequencies of light. In terms of the photon nature of light, different frequencies correspond to different energies. So hydrogen is only giving off certain energies of light. Well, now these look like they form kind of an interesting pattern. We've got one over here, and then a big space here, and then a smaller space, a smaller space, smaller space. These might be described using some kind of mathematical pattern. Well, it turns out actually these are only the lines being given off in the visible part of the electromagnetic spectrum. There are other lines outside the visible part. Well, what do those look like? Here is an image of all of the lines that are emitted by hydrogen, and it's actually on Wikipedia. You can find it there if you'd like. The ones that we can actually see, the lines that we can see, are actually those right here. This is the red line, this is the blue-green line, this is the blue line, and then here's the purple line. That's kind of hard for some people to see. But it turns out that there seem to be a bunch more lines getting closer and closer and closer together as we move over to this edge over here. It looks like there is almost an infinite number of lines in this group right here. Now, obviously there's not really an infinite number. There aren't an infinite number of atoms in our sample of hydrogen. But it certainly looks like there is a very, very large number of lines here. This group of lines is called a series. Now it turns out there are actually other series of lines that kind of look like this one, either compressed together or stretched out. There's another one at shorter wavelengths down here. It looks like this one, but kind of squished together. So we've got one line and then a big space and a smaller space, smaller space, smaller space, and they all kind of crowd in together over here. And there's another series over here where these lines start over here and come together over here. And then there's another series, and another series, and another series. Well, this first series over here at the shortest wavelengths are called the Lyman series. And then the ones we can actually see are in the Balmer series. And then there's the Paschen series and more series. And we're going to take a look if there's any way that we can actually describe these wavelengths mathematically. Knowing what they are experimentally, can we actually describe what those are numerically? We're not trying to explain what causes them yet. Let's just see if we can describe what those wavelengths are. It turns out that the wavelengths of the series form a very simple mathematical pattern. For the Lyman series, we find that 1 over lambda is equal to r, where r is a constant and it has the value, it's called the Rydberg constant, and it has the value of 1.097 times 10 to the 7th inverse meters. Inverse meters to give us the units for 1 over lambda. So r times the quantity 1 minus 1 over n squared, where n has the values of 2, 3, 4, 5, etc., etc. Where that first red line, this is the Lyman series. I'll come back to that, sorry. But these numbers n then number the lines. The wavelength with the longest wavelength was n equals 2. The next line would be n equals 3. You put n equals 3 in here, you find lambda. The next line, you put in n equals 4 and find what lambda is, etc., etc. Then the Balmer series, the one that we could see, that has the relationship of 1 over lambda equals r times it's the same value of r, the same value of the Rydberg constant in this equation, where it's then r times 1 over 4 minus 1 over n squared, but in this case n has the values of 3, 4, 5, etc., etc. Now, this is what I was going to say. In the Balmer series, the first line with the longest wavelength, that's n equals 3. If you put in n equals 3 here, you can calculate the wavelength of the red line, and we'll do that in just a minute. You put n equals 4, and that gives you the next line. That's the blue-green line. You put in n equals 5, and that gives you the next line, which was the blue line. Put in n equals 6, that gives you the purple line, etc., etc. You put in higher values, and you get those lines that all start getting closer and closer and closer. The next is the Paschen series, which has the form of 1 over lambda equals the same Rydberg constant times 1 over 9 minus 1 over n squared, where n has the values of 4, 5, 6, etc., etc. Now, what do we notice, actually? Well, there's a similarity between these equations, and we can maybe even make that a little more obvious if we write 1 as 1 over 1 squared, and then 1/4 is 1 over 2 squared, and 1/9 is 1 over 3 squared. Well, it turns out that we can write a single equation for every line in all of these series. It's 1 over lambda is equal to r, the same Rydberg constant, this value for all of the series, times 1 over m squared minus 1 over n squared, where m and n are both counting numbers, but n is always greater than m. So when m is 1, we have the Lyman series. When m is 2, we have the Balmer series. When m is 3, we have the Paschen series. So m, the label m, tells us what series we're talking about. And then the number for n tells us which line in that series we're talking about. And so this result gives us all of the wavelengths for all of the lines. Now let's stick some numbers in here. Let's let m equal 2 and n equal, that would be 3, sorry, not 1, 3. And see if we get the wavelength for the red line in the Balmer series. So what do we find? Well, with 1 over lambda equals r times 1 over m squared minus 1 over n squared, that is 1.097 times 10 to the 7th inverse meters, times m is 2, so we have 1 over 2 squared, minus n is 3, so we have 1 over 3 squared. We multiply that out and we get 1.52 times 10 to the 6th inverse meters. Taking the inverse of that, we get lambda is 6.56 times 10 to the minus 7th meters, or 656 nanometers and it turns out that is just what the wavelength of that red line is. Now, where does this come from? Can we explain where this equation comes from? Well, let's try. We're going to follow a calculation that was done by Niels Bohr as he modified the Rutherford model of the atom. Now, we're not going to proceed exactly the way he did it, but we're going to go through it using more of the ideas that we have already covered in class. So, let's give it a try.